Hello everyone, I am Saptarshi. I am a software engineer 3 at Google and I have been a competitive programmer. So in this video I'm going to discuss the various problems that came up in Codeforces around 9:30. This video I'll intend to keep it short. Probably I'll keep it focused on the first three or first four problems, and the next video I'll be making on the fifth problem. So yeah, during the contest, as you can see, I could solve the first three problems, and these two problems I could later solve. So a part of D, you can say I had figured out, but the implementation took time, or you can say a lot of time had gone up to the third question. And this question, I managed to find some time today to actually take a look again at it. This is also a good question. The best part about this contest is that this actually pushed me to think harder than many other contests. So this contest actually somehow challenges your implementation skills, your thinking skills, your observation skills in many different ways. So I think even though I'm 2 to 3 days late in publishing this video and this playlist, you should actually find this valuable because there are some really good problems over here. So anyway, let's get started with the first problem out of these six problems in this div 2. So it says that we have a shuffle party. We have an array of n integers. Initially ai is equal to I, and then it says that swap of k basically means that k will get swapped, or kth position will get swapped with dth position, which is the largest divisor of k, which is not equal to k. So AD and AK will be swapped. And the swapping will happen in this order. So from 2 up to n. In this order, the swapping will happen. An integer x is a divisor of y if there exists an integer z such that, okay, this is the divisor definition. So let us see what this means. The problem A basically tells me that let's say our n is equal to 6, or let's say uh, 10. So initially, these are the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At those locations 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. First, what runs is swap of 2. When swap of 2 runs, 2 will say that, so yeah, it runs from 2 up to n. So it says that swap with the greatest integer not equal to 2. So 2's greatest integer not equal to 2 is equal to 1. So you'll swap these two. 2 and 1, these two positions gets, the values at these two positions get swapped. So you get 2 over here, you get 1 over here. Then the turn of this position. So in this way you continue as swap 3 and so on up to swap 10. So when you go to swap 3, 3 gets swapped again with 1. So it becomes 2 and it becomes 3. So I'm basically swapping current value with current value, something like that. And then comes 4, we have to swap this. 4's largest divisor less than 4 is 2. So we will swap these two values, which makes it 4 and 1. And in this way the process continues. So basically 5 will swap with 1, so it becomes 5 over here and 3 over here. And then at the 6 we have 3 as the greatest divisor, so it becomes 2 and this becomes 6. Similarly, it continues for 7 again with 1, so 7 and 5. And so on. It continues through these levels as well. Now, what is the question? The question says, what is the position of 1 in the resulting array? Where will 1 go? If I complete this, 8 with 4, so at 4 we have 1, so 1 comes here, 8 goes here. 9 with 3, so at 3 we have 6, so 9 comes here, 6 goes here. And 10 with 5, so at 5 you have 3, yeah, so 3 goes here and 10 goes here. Quite a lot of changes, but what is the position of 1? That is what we are interested in. 1 is located at 8. And let us see where has 1 come through. 1 first was here. 1 was first located over here. Then 1 came over at position 2, at index 2. Then 1 came to position 4 or index 4. And then 1 came to position 8. This is the way 1 has gone. Why so? Because first when 2 came, 2 said that yes, I'm going to take whatever is there in 1. So after 1, when 2 comes, 1 goes at 2, 1 stays at 2. Next, when 4 comes, 4 will say yes, 2 is my greatest divisor lesser than me. So this 1 goes over here. 3 will not get that 1. 1 goes from 2 to 4. After that, 5, 6 and 7, they don't have 4 as a factor. So 1 cannot go to any of them, 5, 6 and 7. Only when 8 comes, 1 can go there. So whatever is there at 8, we can say, okay, for 8, 4 is the greatest divisor. And so this will go over there, 1 goes over there, and so on. In this way, can you see that it is moving through the powers of 2? So that is essentially the crux of the problem, that okay, it will go to the largest power of 2. We can have 9, 10. Here also you see it stops at 8. So we can go up to 15. None of the numbers up to 15 will have 8 as a divisor, as the greatest divisor or any divisor. So they will not swap with 8. Only when 16 comes, 16 will take up from 8. And then 32 will take up from 16 and so on. So what we need to know is up to our n, what is the maximum power of 2? That is the question, that is indirectly the question over here. So what we need is the maximum power of 2 that is less than equal to n, right? So if we see for 1 it is 1, 2 to the power 0 is 1, for 4 2 to the power 2, 4 is the greatest possible, less than equal to 4, for 5 also 4 is the greatest possible. And for this value we see something like this. If we find out the next power, it will be greater than the given input. So yeah, it is holding for my test cases. So that's what I have implemented. Let's quickly go through the implementation. This was actually the only straightforward problem in a straightforward thing that sort of, okay, you get the idea directly and you implement it directly. Other problems will actually make you think, and that is the purpose behind this video. So let us see. Yeah, there you go. So what I did was I started with the smallest power of 2, that is 1, and then I kept on multiplying as long as it stays within n. If I see that x into 2 is not less than equal to n, I will not do multiplication by 2. So x basically is the largest power of 2 that is less than equal to n. That's it. 2 to 3 lines code. Awesome. So now let's look at the next problem. The problem of binary path. This again is quite an interesting problem because the first few lines tells you what topic this problem is based on. Should be based on. There is a 2 cross n grid. You are moving from the top left to bottom right. Clearly in many people's minds, DP will come automatically. That okay, from the top left to the bottom right, I'm going in 1 step or 2 step, whatever. There is a common DP kind of thing that works in the mind. So what has been asked is find the lexicographically smallest string. In what sense? Each cell has either 0 or 1. Okay, so basically you can see this as one such 2 cross n grid. You have 0 or 1, and now you need to go in some way such that you get the lexicographically smallest string, and you need to say how many ways you can obtain such a lexicographically smallest string. Now you can move only right and downwards. This is important. You can't move upwards. You can move only right or downwards. So let us take this example 1101 1100 to understand the question. 1101 1100. So over here we can see that if we go first down and then to the right, what we will get is 11100. If we first go to the right and then down and then to the right, then also we get the same thing, 11100. If we say okay, we will go 3 steps to the right, then down, then over here, this sky blue thing gives us 11000. Till now this is the best. The top two are the same and they are not as good. And the last one, let us also not skip that. We will go to the extreme right and then down, and that will give us 11010, which is better than the top two but not as good as the sky blue one. So this becomes a good choice for us. 11000 should be the answer. We can check that over here. 11000. Yeah. So now, by looking at this question, straight away DP works in mind that at each position, that at each position, let's say over here, this was our situation, we can say the different ways to come at this location is from the top and from the left. So we can say if we have the answer over here, the answer and number of possibilities, and over here also if we have the answer and number of possibilities, answer 1 num1, answer 2 num2, we can choose the best among them. We can say that okay, answer 1 and answer 2, whichever is the better one, will come over here. So this carries the better answer, the answer dash, let's say, and the better, I mean the corresponding number. Now in case if my answer 1 is equal to answer 2, that means both left and right gives both left and top gives me the same thing. So I will say okay, I'll take the number from both of them. So num1 plus num2 is my total number of possibilities. And how does it really happen for this given example? We can say over here the string till now will be 111. If we come like this, it will be 111. If we come from the top, then also it will be 111. And for this guy, the string will be 110. So at this guy, I'll say we can take from left, we can take from top. We should take from top because the top one is better. So we will say, okay, it's 110. And from the top, you have how many options? You have only one option. Only one way to get 110. So we will say, okay, we will take the answer 1. So in this way, we can have a DP formulation. But there is a big problem in this DP formulation, which is not really in the time complexity of this transition of DP, but because only the number is not important, but we have to propagate the string also. If you look at the string, the size of the string is really interesting. And that is surprising that slightly it sort of appeared that this should be slightly, not what a B question really indicates in a div2 contest. It's slightly harder than that, or slightly trickier than that, we can say. We have to think of something which can fit this size up to 2 into 10 to the power 5. So the thing is, if the size goes up to, if the length, or I think n goes up to 2 into 10 to the power 5, the problem is that from the left, whatever string we are forming, like over here it is 1, over here it is 1 1, over here it is 1 1 0, over here it is 1 1 0 1, it keeps on increasing. And if we take the sum of the lengths of all those strings, the sum of lengths of all the strings that we are storing from left to right, basically is a very big value. This is nearly n square, 2 into 10 to the power 5 square, which is unmanageable. So that is one part. So if I don't store the big number, how can I compare? That is another part. So somehow it tells me that okay, I have to store, if I have to follow this possibility, this kind of thing, that at any point I want to know from the top and from the left, then I need some way. Either I intelligently keep on truncating the left parts, that is the first way out that sort of sparked in my mind, that let's truncate the unnecessary things from the left, whichever are matching. And if there is a big gap between the left and the top, we have to figure out a way to remember only one of them. So if I know that okay, from the top 110 dot 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 something is coming, and from the left 111 something is coming, I should be able to say okay, please forget this entirely, just remember this one, and please don't check the left at all. That kind of thing I have to think of. But the more I thought, it sort of became complex. So then I took a turn over there and I said, okay, is there a way to avoid the DP? What does DP or dynamic programming help us in? Dynamic programming helps us in considering all the possibilities and reaching a solution. So I felt, okay, let's push away dynamic programming. Let's focus on something different. That while I'm moving forward, is it possible to decide whether I can move to the right or to the bottom? If I can decide whether I should move to the right or the bottom, then there is no ambiguity. Now there is another observation over here. This is an important observation. One observation over here is, if I once move down, I cannot go back to the top row. If I once move down, that is a terminal decision kind of thing. So I have to sort of decide, as I move ahead, I have to decide, should we move down? should we move down at any step? Now this, to me, it was a small hint as well as complexity that okay, how to handle this, because if I mean, at every point probably will not get this answer that whether we should move down or not, but sort of I have to move ahead with that. I have to move ahead with the knowledge that okay, we could move down over there, and then at some point of time in the future I have to decide that whether we can move down. But this also gave me a kind of hint that okay, if we have to decide this is the only decision we have to make. If I decide that I'll move down, after that there is nothing to be decided. If I decide that I'll be moving down, after that there is nothing to be decided. I just will complete this way. Which means that the only question, this actually told me that the only question we need to answer is at which I should we move down? At which I should we move down? Should we move down? This is the only question, and there are how many possibilities? There are n possibilities. This made it clear, okay, there are not more possibilities than n possibilities, there are exactly n possibilities. So one way is, okay, take all the possibilities of moving down. Unfortunately, that will also take it to n square. So brute force cannot be applied. This definitely needs tricks. And so let us see through problems, through the test cases, if we can reach something. Now, whatever I did after this was through the test cases. So 0, 0, 0, 0. The first test case, 0, 0, 0, 0. When I am over here, I sort of know that my right and the bottom are the same thing. So I can say, okay, if I move to the right, I have greater flexibility. If I move to the bottom, that means I have no flexibility. I have to move like this till the end. So definitely at this point, I should move to the right because that gives me better flexibility. I can always come down to the same place where this would take me. So okay, I can move to the right, but I have to remember that okay, the bottom also gave me a similar possibility. So I will go to the right and I'll keep in mind that the bottom also gave me a similar possibility. They are the same thing. And then I'll say, okay, no more options. We have to move down. And at this point, I can say, okay, this is one circle. This elliptical thing sort of gives me the idea that there is one possibility to come down over here, which means this is one possibility I came down. Now, this was another possibility I could come down over here. Let me check. Yes, the answer is, I mean, the number of ways is 2. So I can say yes. You have reached here, there definitely one possibility is there, and you had crossed one circle, which basically told you were at the same place. You could have moved down over there. So it's a, you can say one way to say, okay, 1 plus 1 equal to 2. Let us see if the similar approach works in bigger examples. 1101, 1100. So it's 1101, 1100, 1100. Now let us see. I am starting over here. Where can I go, right or down? Both are the same thing. So ideally I can go at both the places. From the top left, I can actually go to both the positions. It means the same to me. From there, I actually have the same access, next position, but I'll be moving in the forward direction because this has access to the front elements which this guy doesn't have. The above one still has access to the top row. So I'll keep on exploring that. I'll see the next one. Next one tells me, okay, there is a difference. 0 and 1, there is a difference. This is the better one. And what does this tell me? This tells me that if I were over here, I could reach over here. If I were over here, I could not reach over here. So I'm saying, okay, I have marked an equality, but now when I move to the next diagonal thing, from this top thing, I know that I have a choice. And when I have a choice, I have a choice and now I have to select only the top one. The bottom one doesn't have a choice. And so this is my situation to say, okay, whatever was pending, we can't take the bottom route. These are not correct routes. We have to only take the top routes. So basically, the moment we saw something better in the top row, this is the case of better in the top row. Whenever there is better in the top row, this tells me that no down movement is allowed before this. No down movement is allowed before this. So basically automatically you come over here forgetting everything that you had recorded till here. Okay, 0. Now for 0, bottom or right? Now it will say yes, now bottom is better. When the bottom is better, now okay. Did you now was there any other scope other than selecting this? No, you would not select this. So to come to this 0, there is only one way from the top. If there were other ways you were recording, then you could have taken that into consideration. But this is the only way. So we will count this and we will say, okay, come down. This is deterministic. This is deterministic. Come down. And when you come down, after that, there is nothing to see. You just move ahead. This is the only thing you get. So see, none of the steps actually tells you have more than one possibility. Here you had a chance, you proceeded forward and you saw that, okay, that was not a possibility. Back to 1, and then you came down, and after this it remains 1. There is no chance. So this particular thing will be our answer, 11000, and the answer is, the count is 1. 11000 and the count is 1. Yeah, count is 1. The last example should make the remaining things clear. 001 001 11 111 01 101. Okay, again starting from the top left. Where can we go? Where should we go? Bottom or right? Definitely to the right. No other choice, definitely to the right. Now, bottom or right? Both are fine. Both give me the same thing. Okay, so let's move ahead. Now, from here, bottom or right? Right. Right means that now you will not consider them as equal. From here, you could not move to that 0. So please forget this. They were not equal. The top root was only better. Fine. From there, bottom or right? They are the same thing. Bottom and right are the same thing. Okay, now next, bottom or right? Again, 1 and 1. Interestingly, again the same thing, 1 and 1. Next, bottom or right? Again, 1, 1, it gives us the same thing. Next, bottom or right? Bottom gives us a better thing. Bottom gives us a better thing, so I'll say I will come to bottom. And when I decide I'll come to bottom, that means from this point only I could have come to this place. From this point also I could have come to this place. From this point also, or over here. I have 4 different ways to come to this particular 0. After this 0, there is no ambiguity. After this 0, we will come to this 1. But up to this 0, I had 4 possibilities, which means that these 3 circles of equal possibilities gave me 3 alternatives, and now I'm able to use those alternatives. I'm able to confirm those alternatives when I reach over here. This is when I say, okay, those 3 alternatives I can use. So basically, when I see a 0 at the bottom, that is when I can say, okay, now, since I'm going to the bottom, I have to go to the bottom. The right one is not so good, or to the right there is nothing, as we saw in this case. To the right we had nothing, so we had to move to the bottom. So whatever equal, circles were pending, we sort of took all of them. So here we had 3 different situations to come down, and this is the 4th situation. So those 3 points at which we marked 3 circles of equal elements to the right and bottom, we will add them to the possibilities. So we can say, okay, 3 different possibilities to reach this 0. So the answer is 3. Sorry, 3 plus 1, 4. 3 plus 1 equal to 4. What is this 3? We were calculating this 3. If let's say instead of this 0, a 1 would have come, and instead of this 1, a 0 would have come, I would have to forget this 3 forever. One other interesting observation is that, okay, I got a similar equal element here, but could I take this? Now should I say that I should be able to take that as well? Never, because this 0 tells me that here the bottom root could never be taken. That 0 is important, and MSB's most significant bits, left bits, are more important than the right bits. So definitely you can't compromise this 0. So in this way, with a greedy approach, this problem can be solved. You can see DP is mentioned in the problem tags. The mind goes over there, so you can use DP, and you can use some implementation tricks to actually be able to accomplish completing the solution. But still, the trick and the nature of the problem and everything, constraints, etc., tells us, this particular thing tells us that okay, you can't maintain it at every step, you have to take up those calls. Now I got a TLE in the first attempt over here. Let me also throw light on what I did in the TLE thing. The algorithm was exactly what I told you just now, but I was maintaining a string. So I was maintaining this string, and to this string I was adding at every step. I was adding at every step what string what character I'll be taking. The bottom character, I mean, this is the top row I plus 1 character, and this is the bottom row I character. And this concatenation to the string actually increase the time complexity, because it's you know it actually takes some time. So how could it be avoided? Instead of appending at every step, we can actually deal with it like a character array, because there is not at all much ambiguity. At ith index, we'll be recording the ith character. So this is how I took care of the TLE. I dealt with the TLE during the contest only. So yeah, I am taking them in this character array A, and then I am basically I did this DP approach first. You can see this DP approach did not go well, and then I proceeded in this way from 0 to n minus 2 actually. So I'm checking the bottom one and the right one. So this one, a0 I plus 1 is the right one, and a1 I is the bottom one. If they are equal, I will say okay, sum plus plus. That means there is that circle which I made over there. That sky blue circle that I made over here. It is that circle. So I'm basically counting. The first time when I encountered, I'll say plus 1. Next time it becomes plus 2. Next time it becomes plus 3. Next time I go down and I record that plus 3. What do I do? If I see that the right one is 0, that means I have to take the right one. And I have to check whether it is equal or not. So if it is not equal and if the right one is 0, that means forget whatever you saw towards the bottom. You are not going to get any benefit out of that. Sum becomes 0. In the sum, I was recording that how many circles I'm getting, how many equals I'm getting. But now sum becomes 0 automatically. And then we record that right character. Else we record the bottom character and we add this sum to the answer. We have these possibilities. Now as I'm adding to the answer, now I'll break because I have come to the bottom row. From the bottom row, there is no such decision to be made. And I'll say, okay, if I equals to n minus 1, which means we have not encountered the break, we have come after this last iteration, then I'll say, okay, add the answer to the sum to the answer. This is the leftover sum that was over here, which will help us in the first case when we had 0, 0, 0, 0. So when the loop ended, then we came out. And then I said, okay, whatever is pending, just add that. Else I plus plus. Else means, this else case means that we ended somewhere over here. We ended over here, so we came down. So we will say, okay, if we have come down, then just basically do I plus plus to go to the next index. And then from there, take all the remaining characters. So it's like this step is mandatory for both the cases. You can say for this case only one character is needed, and for the other cases number of characters are needed. So that's the only thing, and then you have to print. Just print this. This is a character array I used, Ri, and yeah, the answer is the numerical value of count. So that's it. Pretty interesting, pretty tricky, and yeah, it caused a lot of confusion and fun during the contest. A lot of people, solved it eventually. During the contest, you can see 6044. I would say pretty low with respect to problem B. But fine. Now let us move to problem C. Problem C is bitwise operation wizard. For this problem, there is a prerequisite. You need to know bitwise OR and bitwise XOR. You need to know that basic of bit manipulation to be able to understand this problem. Okay, so what does this say? We are given a permutation. We are given means, okay, there is a permutation which is hidden. It's a secret sequence. It's a permutation of 0 to n minus 1. 0 to n minus 1. And now, we can ask queries. We can pick up arbitrary indices A, B, C and D, all of which are from 0 up to n minus 1. And we can ask that, okay, PA or PB. So if we send ABCD, the jury will calculate PA or PB and PC or PD, and we will return the comparison that, okay, whether this first bitwise OR is greater or it is lesser or equal to the second one. Let me take a quick example. 0312. So that is one permutation given to us. 0312. That is one permutation given to us. Now if I ask this query 0231, 0231, at 0 we have 0, at 2 we have 1, at 3 we have 2, at 1 we have 3. If we do OR, 0 or 1 we get 1, 2 or 3 we get 3. So jury will calculate this, the OR of the values at these two positions or at the values at these two positions, and will give us these values 1 and 3, and then we can compare and say, okay, which one is greater? We can say 1 is less than 3, so it will return less than. You can check over here, it will return this less than. We have to input it and we have to take the next steps. Now we can ask this how many times? 3n times. Maximum 3n queries we can ask, and it will return, okay, we have to basically return two indices by the end of this 3n or less queries. We have to give two indices such that pi XOR pj, XOR pj, bitwise XOR, that is maximum possible among all possible pairs. So over here I can say that my answer should be either these two pairs or these two pairs. So basically I have written indices, so it will be these two indices or these two indices. Okay, now so my answer can be either 0, 1 or 2, 3. Let us see, check the answer that's given there. Yeah, it's given 3, 2, 3, 2, 2, 3 are the same thing. So you can return 3, 2 also, you can return 1, 0 also. These are the 4 possible answers for this. Whichever one you return, you can return with an exclamation. That's the way the system understands that you are responding. You are giving the output. Okay, so now how can we solve it? How can we, without knowing the permutation, ask the right queries and get the get those perfect indices? There are so many indices. So where can my n go up to? That is what is interesting to me. First of all, one constraint is less than equal to 3n queries. Next constraint is that the n goes up to 10 to the power 4. N belongs to this range, 2 to 10 to the power 4. Now this is interesting. Usually in these problems, often we see the provision to apply a divide and conquer technique. First of all, bitwise OR and bitwise OR are not the same thing. We have to find out bitwise, those indices such that pi and pj, bitwise XOR will give me the maximum. So how can we use the divide and conquer? If I use the divide and conquer approach, then sort of it comes to that end that, okay, using some pivot, I will distribute the elements. So I will use some comparison. This less than greater than will give me some idea, okay, which is lesser, which is greater. In this way, I'll divide something. I'll get two partitions. In each partition, I'll again divide and so on. Before I do anything, this sort of brings to my mind that, okay, this will lead me to a time complexity of n log n. At the best case, in most cases it's n log n, it's not better than n log n. And in this case it's slightly dangerous because n log n basically means n into log of 10 to the power 4. And if I take to the base 2, that basically brings it to somewhat around 13n. which is difficult to bear because I have only up to 3n. So with this, divide and conquer goes out of the picture. If it becomes better than n, then we can think about it, but not for now. What else can be done? One thing in these problems, the one thing that I frequently do is, can I find out one element? Can I roam around you with these operations and find out one element? The problem is that if I have A, B, C, and D, if I have A, B, C, and D, and I get the less than symbol, that basically means that PA or PB is less than PC or PD. And unfortunately, that doesn't tell me which one leads to the greater one. Let's say this is greater, so whether C is greater or D is greater, and in what way is greater, how many bits that has more, it has how many bits, how many crucial bits, or whatever, or whether it is a contribution of both of them to be bigger than these two. There are lots of questions that come. Maybe PC alone would not be bigger than this, maybe PD alone would not be bigger than this, but together they become bigger than this. It is possible. How do I become sure about the C or D or A or B individually? Because I need those individual things. If two elements together, if I know that PA or PB is equal to the maximum possible, is equal to that max, I cannot say that their XOR will also be equal to the max. I cannot say this. And that is why I need more confidence into what their exact values are. Now, before I proceed further, what is the max value? With basic bit manipulation knowledge, you can understand this, that if your n-1 is a b-bit integer, what I mean is that the the leftmost one, the leftmost one is the bth bit, from the right. So something like this, if n-1 is equal to, let's say n-1 is equal to 13. 13 basically means 1101. So that means it is 0, 1, 2, 3. So if it is 13, for that what can be my expectation of maximum? I can say, okay, there has to be some number 10 which is before this 13. So together they'll give me a maximum of 1, 1, 1, 1 as the XOR. If I take another example, let's say n-1 is equal to 31. 31 basically is 16 plus 8 plus 7, is it? So I'll take a lesser one, let's say 35, which is 32, 16, 8, 4, 2, 1. Yeah. And now the bits are 0, 1, 2, 3, 4, 5. This is the bit that is the largest possible. So in my XOR, what can I expect? Definitely I cannot expect a 1 before this. This is a maximum. Definitely I'll expect this to be 1. And then I'll expect everything to be 1 over here. Is it possible? Definitely it is possible, because we can find a number like this. Now, if you're clear about this, now you know that, okay, with n-1 itself, there exists a number, there exists some x in the range 0 to n-1 such that the XOR will be equal to the maximum. So there exists such a number. If you know that there exists such a number, you can say that means this is a good find. If I am able to find this, that solves half of my problem. If I can find this maximum number that is given to me from my permutation, this n-1 is the maximum number. So that was my first step. The first step over here was to find that maximum number. And how can we find that? So if you have to find that, okay, through these queries, one thing was that in the queries only, the given queries only, it was clear that two of the numbers can be same. A, B, C, D need not be distinct. So one strategy was, okay, we can use that to query something like this 1122. What does this mean? This means that P1 yeah, P1 or P1 and P2 or P2. We can say that okay, whichever one is bigger. So this one ends up being P1, this one ends up being P2 only. So if I get the less verdict, that means it is lesser, P1 is lesser. If I get the greater verdict, that means P1 is greater. If I get the equal verdict, which will not happen. If it was equal, that means P1 is equal to P2. But I know that two elements are always different. So using this trick, by keeping the first two the same and the last two the same, I have got a way to find out which one is bigger, P1 or P2. I have got this way to find out. Now, in this way, I find out the greater among two numbers. Now, using the bigger number and another number, I can find out the greater among those two. So in this way, I'll say, okay, take out the maximum, find out the maximum among the first two numbers. Let's say 1 and 2. And then whichever is the maximum, with that take the maximum of 3. So maximum of m and 3. Then you get something like m2. With that, take the maximum with 4. Then you get some other m3. Take the maximum with 5 and so on. In this way, in how many steps will you get the maximum, the index containing the maximum? You know the maximum, but the index containing the maximum you will get in n-1 steps. Okay. 1/3 of your attempts are gone. Now the next part. If we want a partner of this one, if you want a partner something like this, how can we get? We can again try with all the numbers. So I can say with P1 once again, I will try or whatever you get. Let's say from here the answer that you get is X. Now I'll say okay, X and some other number, some other I, let's say. I want this to be the XOR with that to be the maximum possible. Now for that, the minimum that I need is, first of all, the OR should be maximum. It can happen that the OR is maximum, but still the XOR is lesser because of some common bits. So I was thinking in some wrong ways that, okay, these many bits can be common, these many bits can be different, etc. How can we take all possibilities, etc. But then it took me some time to figure out, okay, what if I find out all those numbers for which this gives me this bitwise OR gives me the maximum value. So first thing that I mentioned is X XOR I needs to be maximum. For this, one requirement is, first requirement is X or Y, X or I needs to be maximum, and X and I should have no common bits. So how can I find that maximum? I can say initially take with 1. So you can say X was this value we obtained. Now you can say X with 1 and then X with 2. Take the OR. So whichever one you get as the better. Let's say you get 1 as the better. So next time you will do, okay, X1 and the next 3. Let's say you get 3 as the better. Over here, let's say you get this one as the better. Let's say you get greater than symbol. Over here, let's say you get lesser than. The next time you will take X3 and compare with X4. In this way, X or something you will get whatever. And here you can get equal sign. Equal sign basically means both 3 and 4 will have the same impact, which means that the third number and the fourth number may have 1 or 2 bits different, may have some bits different, which are already set in X. So it doesn't make any difference. So it basically means that P of 3 and P of 4 vary in those bits which are already set in X. What do we want? Let us understand that through this example. 1 0 0 0 1 1. 1 0 0 0 1 1. What can we say? We can say, okay, if we OR it with this is a number 31 which is less than 35. So this is a valid number. If we do bitwise OR, we will get 1 1 1 1 1 1, which is the best. If we do with 31 minus 2, that is 29. That is, if I do the same thing, sorry, if I do the same thing with 11101, then basically we get 1111 1, because I'm doing OR, so it will be 1 1. So you can see for 31 as well as for 29 I'm getting the same answer. Now what is the best? In this way I'll get some numbers over here. You can say, okay, some indices will basically, I'll get two indices which will point, one will point at 31, another one at 21, and I'll get another number as well from here. I'll get 11100. So in this way, if I compare with all possible xi's, so I'll compare x with the best till now, and with new numbers, with new i's. I will test this for all the i's. I will do this comparison, and I'll reach the inference. Okay, how many i's? For how many i's my OR is the? I'll get the list of those i's for which my OR is the best. I'll get the list of those i's. List of i's such that P of X or P of I is equal to maximum. Now, among all of them, what is different? Among all those PIs, what is different? Only those bits are different which are already set in X. All those PIs only differ in those bits that are already set, in PX. And this gives me the guarantee that which one exactly is my answer. The smallest among them, can I say that will have all those bits as 0. I want all of them to be 0. I want the minimum possible, which will and why so? Because basically this is my number 100011. I will say, okay, I want only these bits to be 1. And since I know that, okay, it is giving the maximum and it is the minimum possible, can I say this will only be the minimum possible among those i's, which will have everything else as 0. So this sort of tells me that this is the minimum. This is the minimum out of all those PIs. And so, in order to find this list of i's, my first step was definitely to get the x. My first step was to get the I, to get the x such that px is equal to n minus 1. For that, the time complexity is, or the number of queries is n minus 1 queries. My second step is to get all the i's such that px or pi is equal to maximum. Maximum basically means whatever is the number of bits, 2 to the power b plus 1 whole minus 1, something like that. Or I'll just write the maximum for the time being. And this again will take me, for all the i's, this will take me n minus 1 or n queries. Or this can actually take n minus 2 queries also, if you omit both the I and the x, if you omit the x and the initial base that you are taking. Initially you will say that, okay, x and 1 is the best. Now with respect to that, you will compare x and 2, x and 3, x and 4, and so on. So n minus 1 or n minus 2 queries, something like that you will need. And then the third is that out of those PIs, you have to find the minimum. Minimum out of those PIs. You know how to find out the maximum, so you also know how to find out the minimum. Here you found out the maximum. This was basically the maximum. So the minimum will follow exactly the opposite strategy. Now you will pick up one of those i's. Let's say these are I1, I2, I3, I4 up to some IK. So it will proceed like this: I1, I1, I2, I2. This will tell us which one is the minimum out of these two. Let's say that is I1, just for example. Then I'll say, okay, I1, I1, I3, I3. Let's say over here I3 is the minimum. Then I'll say, okay, I3, I3, I4, I4, and so on. At the end, whichever one I get, IK, or sorry, uh, I dash, that I dash is my answer. So I will return X and I dash. So how many queries do I need over here for all these PIs? How many maximum PIs will be there? Maximum n minus 1. Though it will be lesser, it should be lesser, but still I'll say, okay, n minus 1 queries in this last stage also. Because can it be n? Okay, let's say it can be n. Let's say all the numbers. All the numbers give us maximum on doing bitwise OR. Possible. So okay, on adding them, n minus 1 plus n minus 1 plus n. This gives us n minus 1, n minus 1, and n gives us 3n minus 2. You can see this was a pretty close threshold that they had given. It can be as a kind of hint that in 3 steps, in 3 whole steps, I mean going through all the numbers, it should be targeted something like that. But you can see usually the range is given slightly higher for this. Maybe some other author might have given in some other time 5n or 10n, something like that, to give flexibility for different algorithms, for other kind of algorithms. But here it's pretty rigid that okay, the best possible is within 3n, so we want that only. So this is one specialty of these countries, that it actually sort of pushes you to bring out the best. So yeah, that is it. So what we understood through these 3 problems is, the first problem pretty much was an observation that we had to look at them, understand how the 1 is transitioning, just focus on that 1. 2, 3, 4 are just distractions for us. Just focus on the 1 and see the trend. That only would suffice to give the observation. 1 is going to 2, and for 2, 2 is the greatest common greatest divisor, less than the number of 4, and 4 is that thing of 8, 8 is that thing of 16, so on. You get the chain. So that was sufficient. When you came to B was quite tricky in the sense that it gave you a DP impression, but then with large constraints, it forced you that see it in a greedy way. That is what greedy does. For larger constraints, you have to employ greedy with extra tricks if necessary. And there are many problems which can be solved using both greedy and DP, and according to the constraints, you have to decide accordingly. So yeah, that was about B. And about C, it's a game of bitwise bit manipulations. For this, what I basically had to keep in mind, you have to basically keep those basics in mind, that okay, my bitwise XOR basically needs me to find out such 2 numbers which will be different at all their bit locations. Getting the maximum as one number is one benefit. It is not necessary. If I tell you in the hardcore way, this is not necessary. It is not necessary to find out this thing. You could have found out a different thing. You could have said, okay, if I know that the leftmost bit is something like this, 100000. Let's say this is the leftmost bit. Then any number greater than equal to this would also solve my problem. I just need one number greater than equal to this, and then I need the minimum number with this. That will basically give me uh, the maximum OR with this. That is it. So if you get any number greater than equal to this and less than equal to the maximum, that will also solve your problem. What is this here? I'm basically taking one is leftmost, maximum bit. That is the leftmost bit in n minus 1. So doing that calculation, that calculation you can do, and you can save some queries over here. Instead of n minus 1 queries, you can end up in less queries, but I think that will be randomized. We can't deterministically say that it will happen in n by 2 or n minus 5 or n minus 10 queries. It will be randomized, but in a randomized way, on average, you can sort of end up in lesser than that. That's the reality. But anyway, that is quite different for different values of n. For n minus 1, which is closer to the nearest power of 2, the lower nearest power of 2, we will have lesser optimization from there. The ones which are farther away from the nearest power of 2, that will have greater optimization. So anyway, it's not, I mean, the only point I want to make is that it is not necessary to find out this maximum, but it is useful over here to find out this maximum. Without finding the exact maximum also, you can improve it, I mean, you can complete it. Probably it won't improve far better than this, but you can complete it at least with these many queries. So yeah, that is what this these three questions teaches us. In the next video, I'll be covering the last, these two problems, D and D. These are quite good problems. There are good learning stuff over here, especially in observation. And also in E, you will find some usage of known graph algorithms and some good implementation practices which can help us solve them to completion. So stay tuned. See you in the next videos, and see you in upcoming Codeforces contests and in these editorials. Take care, keep coding. Please share with folks who you think might find it informative, and see you all in the upcoming sessions. Take care. Bye.